here we're doing some Riemann sums to estimate integrals and some very basic integrals. So we'll jump right in. As always in this video, remember you can skip around. You don't have to watch the whole thing. Skip to just the questions you need. So here we want a left Riemann sum to approximate this integral. And this integral goes from 2 to 13, which is exactly the data we have in the table, right? And it also gives us the intervals we should use. And it just goes sort of column by column in the table. But we're going to use this because they could easily have said, like, go from 2 to 5 as your first interval. So we'll pay attention to what they said here. And so I'll do my change in x first. So 3 minus 2 is going to be my first interval. 5 minus 3 is going to be my second interval. 8 minus 5 is going to be my third interval. And then 13 minus 8 is going to be my fourth one. So these, you guys have done a bunch of these now. These are the widths of my interval, right? And we're making rectangles, so the other thing we need to find the area of our rectangle is our heights. And we are using a left Riemann sum, so we're going to use the leftmost x for each of these. So I'm going to say for my first interval I'm going to use 6, then -2, then -1, then 3. And notice I don't use 9 here. Okay, and then we are just going to do that math. And I'm going to trust that you can punch that into a calculator on your own. And the result here is 14. Alright, next one is very similar. So we're going to use a left Riemann sum to estimate the height of the plant. Notice the y in this table is a derivative. It is growth rate per week. Okay, so we're adding up all the individual changes in growth. Now, this one's somewhat different if the plant is 3 feet tall when you get it. Okay, so we don't need that number right away, but we are going to need to use that number, right? Because we want a total height, so we're going to do 3 feet plus whatever we get here, right? Because how tall the plant is going to be how tall it is when it starts, plus all of the changes to the height of the plant. Okay, so we're going to use a left Riemann sum, and I actually didn't give you how many subintervals to use, but we'll use them all, right? So we'll do 4 minus 2, 5 minus 4, and then 8 minus 5, and then 10 minus 8. So these are going to be our changes in x. And then these are also like the widths of a rectangle, right? We're going to need the height of a rectangle. It is a left Riemann sum again, so we're going to use the left-hand y value. So 1, 0.8, 0.7, and 0.4. And these are all positive this time. And then, again, we don't use that last one. For a right Riemann sum, right, we would use all of them except for 1.0. And then, again, I trust you to do this math. The result that I get here is 5.7 feet. Okay. Now the temptation, and I bet some of you did this, the temptation is to say the plant is 5.7 feet tall. But this is not the height of the plant. This number, and this is an important understanding that I'm trying to develop for you guys, this number is the total growth, an estimate of the total growth from week 2 to week 10. Okay, so what I need to do to get my final answer for this particular problem, because it wants the height and not the total change, so I need to take my starting height and add the growth. So 8.7 feet is my solution here. Okay, next one, really the next two look sort of intimidating, but they're actually much easier than you think they are. So take a second, read this one, and really think about it. sine is an antiderivative for f. Okay, so if this were like, just as an example, something like x squared, what I would do, right, is I would take the antiderivative of that, and then I would plug in my bounds, right, from 1 to 2. So this, my x cubed, is my antiderivative, right? So what they're saying here, we don't know what f is, but we know that this step in my process is given by this here. So they've actually done the work for us and just made it look harder when it's actually easier. So what we have here, this integral is going to be equal to sine of 1 over x squared plus 1. And then we're going to evaluate it from 1 to 2. Okay? Because it's an antiderivative, right? So the derivative of this would give me whatever f is. And we could actually figure out what f is by taking this derivative. It's kind of an ugly one though. Now we're just going to plug it in. So we're going to do sine of 1 over 2 squared plus 1 minus sine of 1 over 1 squared plus 1. So this ends up being sine 4 plus 1 on the bottom, so 1 over 5 minus sine 1 over 2. And then this is a calculator problem, so at this point we would probably just type it in, and the result we get is negative 0.281. So that is the choice I'm picking there. Okay, so looks scary, actually easy. That's sort of the theme with this next one too. Very similar problems actually. So here we have a table, and the table gives us all these numbers. I want the value of the following integral. Well, when we integrate, we don't know what f prime or f is, but we know when we integrate, we're going to get the antiderivative of f prime. Well, the antiderivative of f prime is just f, by pretty much definition, right? So we are going to evaluate f of x from negative 4 to negative 1. Well, conveniently, we have these in the table, right? We actually don't need this row at all. So what that's going to look like, right, is top minus bottom, so f of negative 1 minus f of negative. So pay attention to the order and the signs here. So we're going to get negative 1.5 minus 0.75. And then the result here is negative 2.25. Okay. And notice if you gotten that order backwards, you would have gotten one of the wrong choices here. Okay. So those two questions were both questions that were looking challenging, but actually easier than even just like if I gave you the function and having you find the integral, because they've done some of the steps for you. You just have to think about what information you have. Last one. Here we want a Riemann sum. All left Riemann sum here. I didn't do that on purpose. So we want a Riemann sum. We're given now the function. We have the integral from 0 to 2. We have 4 subintervals. So you can do this little formula that we saw in earlier lessons, 2 minus 0 over 4. So the bounds over 4 different subintervals. This is going to give you 0.5. That means our change in x is going to be 0.5 each time. So we're going to go from 0 to 2, changing by 0.5. So our x's are going to be 0, 0.5, 1, 1.5, 2. Okay, so we're going to evaluate each of these using the function. And, well, let's see here. 9 to the 0 is 1. 9 to the 0.5, that's the same as the square root, is 3. 9 to the 1 is 9. We know 9 squared is 81. Okay. 9 to the 1.5. Okay, so that's the interesting one. So 9 to the 1.5 is 9 to the 3/2. And by our exponents rules, this is the same as square root of 9 to the 3rd. Which, there's a couple different ways we could do this. We could do this without a calculator completely if we recognize that, well, this is the same as 3 squared to the 3rd, which is the same as just 3 to the 3rd, which is 27. Okay? So, if you're watching this in 2021, you don't need to worry about doing that without a calculator in the exam, but the point is, you could have, right, just by using your exponent rules to figure out what that 1.5 power is. All right, and then we're just going to find a left Riemann sum, so we're going to do, our subintervals are 0.5 each time. So that gives us 0.5, and then we're going to use 1 as our height, because it's the left-hand edge of that rectangle. Then 0.5 again. So change in x times 3. Then 0.5 again times 9. 0.5 again times 27. And the easiest way to do this is notice that 0.5 is a common factor. I'm left with 1 plus 3 plus 9 plus 27, which to me is a satisfying pattern. These add up to 40 on the inside, so 0.5 times 40. My result is 20 is my Riemann sum. Okay, so that is my estimate, and let's see, it is a left Riemann sum, and f. So we could graph this, I guess, if we wanted to. F is obviously increasing, though. We can see from the table 1, 3, 9, 27, 81. Or we just note that it's an exponential function, and this is going to get bigger as x gets bigger. So this is an overestimate. Did I say over? This is an underestimate. Okay, so our graph would look something like this, with all of our rectangles being touching on the left-hand side of the rectangle and being kind of underneath.